Up until now, all of the waves that we've looked at have been called one-dimensional waves. And all that means is that particles in the wave are moving either up and down or they're moving side to side. Okay, that's called one-dimensional waves. And in the second section of our waves unit, we're going to move on to two-dimensional waves. So we're going to show what that looks like, but just as a reference, I want to put down a one-dimensional wave here. So this is what we would see as a one-dimensional waveform. Each particle on this wave, since this is a transverse wave, here's a particle, it's just moving straight up and down. That's the type of motion it has, and that's what we mean by one-dimensional. It's got one plane of motion. Now when we look at two-dimensional waves, think of the normal waves in your experience. So if you've ever been to a lake or the ocean or something like that, you've stood in the waves, and you know that as the waves crash against you, that not only is there a line of particles, of water particles, moving up and down and kind of back and forth as well, but there's a whole width to it as well. So that's what we mean by two dimensions, that each particle is moving back and forth or up and down, or in the case of water waves, they kind of do both, but there's also particles next to that set of waves. So it's like you've got a whole bunch of these strings of particles, but they're all layered next to each other. So there's a width to it as well. Okay, so let me just draw a couple things before we get into what those blanks are. So let's say that you are above the ocean looking down on the waves. What you would see is a set of what we call wave fronts. So you would probably see the tops of the waves because they're kind of the lightest. Lightest in color, I mean, not lightest in mass or something. Okay, so here are our wave fronts, and they are all going to be moving this way toward the shore. Okay, so you're watching energy moving from way out over here, and it's moving this way, and that movement of energy is seen by the movement of the water up and down and slightly back and forth. Water waves are kind of a combination of transverse and longitudinal waves. Okay, now we would call these guys wave fronts. Wave fronts. Okay, now if you would look at this set of wave fronts from the side, let's say you had a sheet of glass here or something like that, and you could stand beside that sheet of glass on the ground and look at the side of these waves. What you would see then is something like this. Here's a crest and a trough and a crest and a trough and a crest and a trough and a crest. Something like that. Okay, so this is our side view, and this is what we would be looking at in a one-dimensional wave, but in reality, this has some width to it. It goes back this way. And so then when you look at it from a top view, you get a crest here, and a trough, and a crest, and a trough, or a crest, and a trough, and a crest, and a trough. Okay, and so this is a two-dimensional wave. So we have to talk about it a little bit differently. The parts aren't exactly the same. Yes, it still has crests. That would be a crest. And it still has troughs. That in there would be a trough. But because it now has a width to it as well, and not just an amplitude and a wavelength, we also talk about the wave fronts. Okay, this red thing that I've drawn over here, this isn't really part of the wave at all. It's just showing the direction of motion, or we would call that propagation. Propagation is the wave moving, or rather the energy moving through the waves. It's the direction of travel. So we would call this red arrow the wave ray. Okay, so the wave ray shows the direction of travel or propagation. I'm going to write that word just so you know how to spell it. Propagation. Okay, so these are the parts of a two-dimensional wave. Now, imagine that you dropped a pebble into a pond. Okay, so then you would have, when you drop the pebble, you'd have this center part. You would have created a trough, at first at least. It would have created kind of a trough as the pebble broke through the surface of the water. And then as that water came back up after the rock passed it, it would then turn into a crest. Okay, and so then that energy that you gave by dropping the pebble into the water would radiate outward. And you know that if you've ever looked at ripples. And so they start looking like this. And this is exactly the same as watching waves in the ocean, or rather it would be labeled exactly the same. So in this case, the direction of travel, or the wave ray, would be like this. The waves are traveling outward. But it would also be traveling this way, and this way, and this way. And really you could draw an innumerable wave rays on this thing, but this is good enough. Okay, and so the wave rays are showing that these waves are expanding outward. So now, if we wanted to draw what the wave fronts were, that would be this thing. This is a wave front. Okay, but wave fronts are not just the very leading edge of the waves that we're drawing. That's a wave front. This is also a wave front. This is also a wave front. Okay, all of those lines that are kind of the reference for where our waves start, those are all called wave fronts. And so just like on the other one, the ocean waves, this black line would be a crest. And this space in the middle here would be a trough. So a wave front is the leading edge of a wave. Usually we would call it a crest. We would label a crest the wave front, but you could make it a trough, and that's not a problem. It is either a crest or a trough. There aren't really any other options. You wouldn't label some point in between a crest and a trough as the wave front. It just wouldn't be practical. We also said the direction of travel is shown by a wave ray. And the wave ray is drawn perpendicular to the wave front. Okay, it always happens that way. Waves always travel perpendicular to their width. Now that maybe doesn't make sense if you're just thinking of that sentence, but if you think of this as the width of the waves are always going to be traveling this way, perpendicular to the wave fronts. Same thing over here. The waves are traveling this way. That's perpendicular to the wave front. Now a lot of what we're going to do in this second section has to do with how waves behave when something happens to them, when they bounce off something, when they move from one medium to another, when they encounter other waves, things like that. And so we're going to look at, first of all, reflection, because reflection is probably the simplest version. So what we have here is some sort of barrier. That's what this solid black line is. It's a barrier, something for waves to bounce off of. And this dotted line here, this is called a normal, or the normal line. If you remember the normal force is a support force from a surface that's always exerted perpendicular to the surface. And that's what the word normal means. It means perpendicular to something else. And so this normal line is just a reference line that's perpendicular to the barrier. That's it. Nothing special about it. So let's look at some waves coming in. I'm going to make them blue. So we've got some wave fronts traveling toward the barrier at an angle. Let's say like this. Okay, and I'm going to use red for the wave ray. So perpendicular to these wave fronts is something like that. So the waves are traveling this way toward the barrier. They're going to strike the barrier, and then they're going to reflect off the barrier. Okay, you may not have actually had experience with this a lot before, but let's say you're in a swimming pool and you've made some sort of wave toward the edge. When it bounces off the wall, it's going to bounce back at you. But if you would push water at an angle against the wall, it would reflect off the wall and not bounce back at you. You probably haven't experienced that. It's going to bounce in the opposite direction. It's going to reflect off the wall in the same way that you sent it to the wall. Okay, and so you're going to find that it instead goes like this. Drawing the wave ray first is going to be the easiest. And so we have this type of thing happening. Okay, so the waves that were coming in this direction bounced off the barrier and then left in this direction. Now we can describe those directions using the angles of incidence and angles of reflection. Okay, so angle of incidence. Incidence means incoming. And so the angle of incidence is defined as the angle between the wave ray, the direction that it's moving, and the normal line to the barrier. Okay, so this thing over here would be called theta I. Okay, sometimes we change that to be theta 1 and theta 2, because later on when we talk about refraction, not reflection, but refraction, we're going to use very similar variables, and we don't want to get confused. But this is the angle of incidence. Now I'm going to write down that word so you can see what it looks like. Incidence. Okay, that means incoming. You can think of it that way. And then this angle over here, let's use a different color. This angle over here is theta R, or the angle of reflection. Okay, so what the law of reflection says is that the angle of incidence is equal to the angle of reflection. So however it reached the barrier, it's going to bounce off at that same angle. So if it came in at a really steep angle, something like this, it would bounce off at that same angle. It's not going to come in at a steep angle and then all of a sudden bounce straight this way. That doesn't make much sense, right? And that wouldn't match our experience either, or what we would expect. So it states the angle of incidence, it would be helpful if I could write straight, is equal to the angle of reflection. And when reflection occurs, the wavelength and the speed stay the same. Nothing changes about the waves. It's not like they get longer or faster or anything like that. So the speed and wavelength, they stay the same. Now we mention that here because when we talk about refraction, those things are going to change.